For decades, hydrologists have relied on a simple assumption when modeling floods and runoff. The past is a reliable guide to the future. In technical terms, this assumption is called stationarity. But what if the statistical behavior of rainfall and runoff is changing over time? In fact, many hydrologists now argue that the stationarity is dead. In this video, I will explain what non-stationarity means in rainfall-runoff process, what causes it, how we can detect it, and what engineers should do about it in practice. Stay with me. Rainfall-runoff models form the foundation of flood forecasting, infrastructure design, and water resources planning. Traditionally, these models assume stationarity, meaning the statistical properties of hydrological processes remain constant over time. Under this assumption, we can calibrate models using historical data and confidently apply them to predict future floods. But increasing evidence shows that this assumption is often violated. When this happens, models calibrated on historical data may systematically underestimate future risks, leading to serious implications for infrastructure safety and water management. Non-stationarity occurs when one or more statistical properties of a hydrological time series change over time. In rainfall-runoff modeling, this can appear in several ways. First, trend non-stationarity, where the mean value gradually increases or decreases. For example, rainfall intensities may increase as the atmosphere warms. Second, shift non-stationarity, where abrupt changes occur, such as when urbanization suddenly increases runoff coefficient. Third, variance non-stationarity, where the variability or frequency of extreme events changes. Fourth, distributional changes, where the overall shape of the probability distribution evolves. And finally, covariance changes, where correlation structure changes over time, such as altered persistence in soil moisture states. Several processes can drive non-stationarity in hydrological systems. The first and most widely discussed is climate change. Rising temperature influences atmospheric moisture and energy balance, which can lead to more intense rainfall events, altered storm patterns, and increased variability in precipitation. The second major driver is land use change. Urbanization increases impervious surfaces, reduces infiltration, and accelerates runoff response. Deforestation and agricultural expansion, on the other hand, can reduce rainfall interception, changing evapotranspiration and infiltration processes. The third driver is water resources development. Human infrastructures such as reservoirs, dams, and water abstractions alter natural flow regimes. These interventions can significantly change downstream hydrological behavior, introducing new dynamics into the rainfall-runoff process. Detecting non-stationarity usually begins with visual inspection. Plotting time series or calculating moving averages can reveal trends or shifts, although these methods are subjective. More rigorous approaches rely on statistical tests. One of the most widely used methods is the Mann-Kendall trend test, which detects monotonic trends in hydrological time series. Other famous techniques are double mass curve analysis and sliding window calibration. Importantly, we must distinguish between statistical significance and practical significance. A trend may be statistically detectable, but is still too small to affect engineering design. So, what should practitioners do? First, test historical data for trends and shifts before assuming stationarity. Second, consider giving more weight to recent data or using moving window calibration approaches. Third, use a split sample validation to check whether model performance deteriorates over time. Fourth, incorporate climate projections and land use changes when estimating design floods. Fifth, adopt adaptive infrastructure design, allowing capacity upgrades if future risks increase. And finally, always quantify uncertainty and acknowledge the possibility of non-stationarity behavior in your analysis. The assumption of stationarity has long been a cornerstone of hydrological modeling. But in a world of changing climate, evolving landscapes, and increasing human intervention, this assumption is becoming increasingly fragile. Recognizing and addressing non-stationarity is now essential for reliable flood prediction, resilient infrastructure design, and sustainable water resources management. If you found this video helpful, please subscribe to the channel for more videos like this. Thank you for watching, and I will look forward to seeing you in the next one.